Hi, this lesson is about rates of change in the natural and social sciences. Applications of average rates of change and instantaneous rates of change exist in physics, chemistry, biology, economics, as well as other sciences. Remember that an instantaneous rate of change is a derivative. So let's talk in more detail about these different sciences as well as business examples of where you would see average rates of change and instantaneous rates of change. So the most common one in physics is when we're talking about the displacement or the position of a particle moving in a straight line, also called rectilinear motion. S of t is a common way to state that type of function. So the change in S over the change in T, which is basically a slope calculation, is your average velocity. So change in position over a change in time will give you the average velocity of a particle over some time period. The derivative of S, which is S prime or ds dt, is what we call our instantaneous velocity or instantaneous rate of change of velocity. But remember, you can also take the derivative of your velocity, and that will give you your acceleration, instantaneous rate of acceleration. And the average acceleration is found by doing change in velocity over change in time. So all of these represent slopes. If you think about this from a graphical perspective, way back when we started talking about graphs and slopes and so forth, this is like a typical slope calculation as well as this one. You have 2 points. You do the change in the dependent variable divided by the change in the independent variable. And the other two would be your derivatives. And remember, a derivative represents a slope of a tangent line when you're looking at it from a graphical perspective. So tangent line means there's only 1 point. So you can't do a change in 2 points over another. So we use the derivative to calculate these, the instantaneous velocity and instantaneous acceleration. So one thing to keep in mind is that the total distance traveled is the absolute value of your displacement function. So distance is positive. And then there'll be also other things to keep in mind in future lessons when we have to take the absolute value when we're computing derivatives and things like that. For now, we're just sticking with these basic concepts. Then chemistry, here's an example. If we let C of T be the concentration of a chemical, then the change in the concentration over the change in time is the average rate of reaction on that chemical over some time period. And the dc dt is the derivative, which is the instantaneous rate of reaction on that chemical. Again, we're using calculus here to compute the derivative. Now we move on to an example in biology. Let's let n equal f of t. So again, it's a function of time, which represents the number of individuals in an animal or plant population. The change in n over the change in t will be the average growth over a time period. So growth meaning the animals or plant population could be increasing, but it could also be a decrease in that growth. And then D, and this should be an F, sorry about that, df dt will be the instantaneous rate of growth. Again, it is a derivative, so that's the rate of growth at a moment of time. Okay, so let's move on to economics. So there's actually quite a bit of calculus in economics, so if you're interested in that, something to look into. So let's let C of X equal the total cost that a company incurs to produce X units of a commodity. Okay, so C of X represents the cost to produce X units of some commodity or product. dC over dx is the average rate of change of cost. So when you produce one commodity and then more of that commodity, there's going to be some sort of change in cost for producing from commodity 1 to commodity 2, for example. And so again, that's like a typical slope calculation. But then we have dC dx, which is the instantaneous rate of cost on a particular commodity. So what's your instantaneous cost on commodity number 1 or on commodity number 5? So a single commodity that you're producing, and that has its own special name. It's called marginal cost in the business world. All right, so let's do an example. The position of a particle is given by S of t equal to t cubed minus 6t squared plus 9t, where S of t is measured in meters and t is in seconds. Part A, we want to find the velocity at time t, so we're looking for a general function for velocity. In part B, we want to determine when the particle is at rest. All right, so let's deal with part A first. So we need to find the velocity, and that means we're taking the derivative of displacement, so we can use our power rule. So the velocity function is 3t squared minus 12t plus 9. Anything regarding velocity in this particular problem, the units is going to be in meters per second because displacement is in meters, time is in. Okay, but now part B is asking us to find when is the particle at rest? So when is the particle at rest? That would be when the velocity is 0. And so what we need to figure out is what's time? What is the time, the solution for time in this equation? So here is our velocity function that we found in part A. We set it equal to 0. It's got a common factor of 3, so I factored that out. I'm left with t squared minus 4t plus 3, that's factorable, so I get this. 3 times t minus 1 and times t minus 3, which means I have two solutions to this equation, 1 and 3. And so that means that the particle is at rest at 1 second and then again at 3 seconds. Okay, so let's do another example. A company makes computer chips from square wafers of silicone. It wants to keep the side length of a wafer very close to 11 millimeters. And it wants to know how the area A of X of a wafer changes when the side of length X changes. So we want to know the instantaneous rate of change of area when the side changes. Okay, so you need a formula. We know it's a square, so that means that both sides are equal. So if I let the side be x, as stated here, area is a function of x, my formula is a of x is x squared. Okay, the derivative is very straightforward, power rule. A prime of x is equal to 2x. But then remember that x is given to be 11 millimeters. So at x equal to 11, a prime of 11 is 22. The area is changing at 22 millimeters squared per millimeter. Okay, so let's move on to our third and final example. I have a spherical balloon is being inflated. Find the rate of increase of the surface area with respect to the radius r when r is equal to 3 feet. Okay, so surface area of a spherical balloon, meaning it's round, it's not what a typical balloon looks like, is S equal to 4 pi r squared. So an interesting kind of side note for you to keep in mind is that the volume of a sphere is 4/3 pi r cubed. And if you take the derivative of this, remember r is your variable and the 4/3 pi is the coefficient. is with power rule, you would multiply by 3 times 4/3 pi, subtract 1 from the exponent. The 3's cancel, and my v prime is actually my surface area formula, 4 pi r squared. So a lot of people know that formula just from high school or middle school. If you can't remember your surface area formula, it's pretty easy to derive by just taking the derivative. Okay, so getting back to the problem, I need to find out what the instantaneous rate of change, right? And so we can see it's increasing of the surface area with respect to the radius r. So I have to find s prime. So s prime is equal to, using power rule again, is 4 pi r squared. And then you're told that r is equal to 3. So you plug in 3 for r, and you get 24. And remember, surface area would be in feet squared because your radius is in feet. So it is changing, the surface area is changing at 24 feet squared per foot. And that's, again, per the unit of measure for radius, because it's changing with respect to the radius r. Okay, so that's it for that lesson. Give the homework a try. Good luck.